12, I'm going to go through some of the questions from exercise 6.2. I did question 31 on the board last lesson, so there is a solution, a written solution up of that, which you can check out. I'm going to do questions 32, 33, 34 and 35. So when you're doing these, I suggest very strongly that you draw a diagram to help you work them out, and then try and work through the information that they give you to try and solve it. So what do we have here in 32? We have an observer sees a plane directly overhead, so vertically, 2 kilometres. The plane is moving horizontally at a constant speed of 500 kilometres per hour. Find the rate at which the distance will be increasing between the observer and the plane when the distance between them is 5 kilometres. So let's get a diagram here. So we have this observer and we have a plane. Now originally the plane was 2 kilometres overhead, directly. But the plane is now moving in a horizontal direction. And we have the distance between the observer and the plane. So let's mark in what we know. That's 2. We'll call that D for the distance. And this is going to be the horizontal distance. So D is the distance between the observer and the plane. X is the horizontal distance. Well, first of all, we need an equation. And we're about finding the rate of change of distance. So we need the D to be the subject of the equation. So let's start with that. So D equals, well, this is Pythagoras here, the square root of x squared plus 2 squared, which equals the square root of x squared plus 4. And we'll write that in index notation, x squared plus 4 to the half. Now, you know that you're going to have to differentiate one of these. So I'm going to start by doing this. dd dx, I'm going to differentiate this. So I'll pull the half out the front. X squared plus 4. Subtract 1 from the power, minus a half. And multiply by what's inside, the derivative of what's inside. So to multiply by 2x. The 2's will cancel out. So I'm left with x on the square root, because that's what that is, x squared plus 4. And that's d dx. Well, what other information did they tell us? Well, they told us that that horizontal distance has a rate of 500. So dx, and because it's a rate in time, dx dt equals 500 kilometres per hour. Now, what do I want? Well, I want the rate of change of d, the distance between the observer and the plane. So I'm going to find dd dt. And I've got all the information here that I need because I've got dd dx, I've got dx dt, and I can just use the chain rule. So dd dx is x on the square root of x squared plus 4 times dx dt is 500. So if I go over here, dd dt equals 500 x on square root of x squared plus 4. Now what did the question ask? It said, find the distance, find the rate when the distance between the observer and the plane between them is 5 kilometres. Now, we've got it all in terms of x, but I can find, look over here, I can find d given x. So when the distance is 5, so I'll just quickly go up here and go d equals the square root. I'm going to put 5 in, 5 equals the square root of x squared plus 2 plus 4. Square both sides, 25 equals x squared plus 4 minus the 4, 21 equals x squared, root 21 equals x. And now I'll just put that in. 500 times root 21 over the square root, well, x squared is 21 plus 4. And I pump that into my calculator, or I can even take it a bit further. 500 root 21, well, so that's going to be the square root of 25, which is 5. And I get 458 kilometres per hour, because it's a rate, it's a change in distance over time. And that's a correct answer. Woohoo! So have a look at what we did. We drew a diagram, we got an equation for d, we differentiated that and got d dx. I've got the rate of the change of the horizontal distance, it's 500 kilometres per hour, that's the speed of the plane. I've found the rate of change of distance between the observer and the plane, d dt. Then I got that stumbling block because they told me find the rate of change when d is equal to 5. And I didn't have d in my equation, but I can find d in the original equation just by rearranging it. Okay, the next question. Well, hey, everyone goes crazy for a kite. A kite, 20 metres high, is blown along horizontally at 3 metres per second by the wind. What is the rate? At what rate is a string being let out when it's 40 metres long? This sounds like it's going to be exactly the same. So let's draw a diagram. There's a kite. First we need is an observer. Oh, here's someone down here thinking very deeply about this. So we'll draw a diagram again. And again, we know, and it doesn't matter which way your triangle goes, which is why I've done this one this way, because it doesn't matter. So we're going to have Pythagoras again, and we're going to have this sort of triangle set up. And that's going to be our D. And that's going to be, what will we call this? Well, let's go with X again. And this height, well, it was 20. The kite was 20. And the kite's moving along horizontally in that direction. So let's get an equation here. Let's get an equation for this. So D equals the square root of x squared plus 20 squared. X squared plus 400. Now we know we're going to differentiate that. So we'll write it in index notation. X squared plus 400 to the half. So this is very much like the earlier question. And we'll get dd dx is a half x squared plus 400, take 1 off the power, minus a half, times 2x. And again, those 2's are going to cancel, which makes it nice and easy. So we get, and we'll write it in surd form, x on the square root of x squared plus 400. Okay, so we've got D. We know that dx dt is 3 meters per second. It's the only difference, we've got different units now. We also need to find out when d is 40, what x is. So 40 equals the square root of x squared plus 400. 1600, we square both sides, equals x squared plus 400. Which will give us 1200 equals x squared. Therefore, x equals the square root of 1200. And because we're talking distances, we only take the positive. All right, what do we need to find? We need to find dd dt. Well, we've got dd dx, and we've got dx dt, so we're away. Now, dd dt, or dd dx, sorry, is x on the square root of x squared plus 400. And dx dt is 3, so I'm just going to put a 3 in front of that. Makes it nice and easy. When the distance is 40, that's when x equals root 1200. So dd dt equals 3 root 1200 over the square root. Now, this is interesting. When I put 1200 into that, I'm just going to get 40 on the bottom. I'm going to get 1200 plus 400, because that's what x squared and the 20 squared is, which gives me 3 root 1200 on 40. And if I pump that into my calculator, it will give me 2.598 meters per second. So there's two that require you to use Pythagoras. Now, you may have been able to write it in terms of d, but I found that method pretty easy. All right, let's go to the next one. What do we got here? A spherical bath oil capsule dissolves in a bath so that its decrease in volume is proportional to its surface area. Its shape remains spherical. So imagine you've got a bath bomb, you put it in the bath, and it keeps shrinking at the rate so that its volume and surface area are proportional, and it retains its shape as a sphere. Show that the radius of the capsule will decrease at a constant rate. So we're going to show that the dr dt equals k, or a constant c. It doesn't matter. All right, so it's hard to draw a diagram for this, so I've just got a picture of a bath bomb there. What do we know? We know that dv dt is proportional. Now, if you don't do physics, that's a sign for proportional to its surface area. Let's just read that again, make sure we know. Its decrease in volume, so dv dt, is proportional to its surface area. Now, as soon as you know something is proportional, you know that that will equal dv dt equals, because it's going down at it's some constant, so I'll put in k times the surface area. Now, what do we know? We know volume is 4/3 pi r cubed, and dv dr is 4 pi r squared. Now, we've got dv dt, we've got dv dr. We need to find dr dt. So I think I'm going to have to turn this upside down. So dr dv equals 1 over 4 pi r squared. Now let's see what we've got. We want dr dt, and we want to show that it's a constant. So dr dt equals dv dt times dr dv, which is some constant, times the surface area, all right, times 1 on 4 pi r squared. Well, we haven't got the surface area yet. The surface area is 4 pi r squared. Now look at that. You can almost see that it's going to be a constant. The surface area of a sphere. Okay, so let's go back here. So dr dt equals some constant times the surface area, 4 pi r squared, times dr dv, which we know is 1 over 4 pi r squared. That's all going to cancel with that, leaving us with a constant. Hence, dr dt is constant, which is what we had to show. Show that the radius will decrease at a constant rate, and we just did. That's a really interesting relationship between the volume and surface area of a sphere. The surface area is the derivative of the volume. I'll let you think about that, and we might discuss it in class. Now the last one, because I'm not going to do 36. A chute drops sand at a constant rate of 8 meters cubed per minute. So we've got this big chute dropping 8 meters cubed of sand per minute. As the sand falls to the ground, it forms a cone, such that the height of the cone is twice the radius. Okay, so I'm going to draw a diagram, but this is the sort of thing we're looking at. We've got a chute and it's dropping sand at 8 cubic meters. So let's draw ourselves a cone now and put our measurements in. And we've got a height and a radius. What do they tell us about the height and the radius? Find the rate at which the height of sand will be changed into tubular space when its height is 2 meters. And it says here, such that the height of the cone is twice the radius. Such that the height of the cone is twice the radius. Well, that's r, and that's going to be 2r. Well, let's go. Let's work on this one. The volume equals 1/3 pi r squared times the height. But we know the height is 2r. So 1/3 pi r squared times 2r, which gives me 2/3 pi r cubed. Well, the first thing I would suggest doing, let's find the rate of dVdr. And that means we'll get 3 times 2/3 pi r squared. And of course, the 3's will cancel, which is neat, getting rid of that fraction. So dVdr, the rate of change of volume with respect to the radius, is 2 pi r squared. Well, what else do we know? We know that the volume, dV/dt of this, is 8 meters cubed per minute. Should probably put the I in there, per minute. What do we need? Let's go back to the question and see, what did they ask? Find the rate at which the height of sand will be changed into 2 decimal places when its height. Well, I'm going to, here, I'm just going to find dVdt. So dVdt equals, not dVdt, oh well, no, if I can say that dVdt equals dVdr times dr dv. Sorry, dr dt. So I'm going to find the rate of change here of dr dt by using the other two. So dVdt is 8. dVdr is 2 pi r squared. And that's what I'm trying to find, dr dt. So I divide the 2 pi r squared, which means I get 8 on 2 pi r squared equals dr dt, which is what I'm looking for, which gives me 4 on pi r squared. There's my dr dt. Now, when was it 4? Find the rate at which the height of sand will be changed into 2 decimal places when its height is 2. Okay. When the height is 2, well, r equals 1 because the height is twice the radius. Now, dr dt, which I have over here, dr dt equals 4 on pi r squared, and when r equals 1, dr dt equals 4 on pi, because 1 squared. Now what do we want? We want dh dr. dh dr. Well, we know that h equals 2r, so dh dr is 2. So what do we got now? What do we need to find? dh dt. Well, dh dt will equal dh dr times, will equal dr dh. Sorry, no, I was right. dh dr times dr dt. And we've got those two. So dh dr is 2 times 4 on pi, which gives me 8 on pi, or as a decimal, 2.55 meters. And remember, it's a height, we're in meters per minute. Now that was a lot harder. It required a little bit more time and thinking, especially to get out this one, to get dr dt, and then here again to differentiate dh with respect to r. All right, hopefully you've been able to work through some of those on your own, and you'll be ready for the next lesson when we come to class next. Good luck.